Okay, I think that's most people joined now. So first of all, welcome to this week's edition of the ARCHER2 webinar series. My name is James Richings. I will be sort of helping to chair this session. This week we're lucky enough to have Mirco Magnini, Gabriele from the University of Nottingham, Edward Smith from Brunel University London, and our very own Gavin Pringle from EPCC here in Edinburgh, going to discuss coupling LAMMPS and OpenFOAM for multi-scale models. With that, I will hand over to our first speaker.
Thank you very much, James, for your introduction. First of all, thank you very much to the EPCC team to offer us the chance to present our work. What we are presenting is the result of a project that has been funded by the ECSC called ARCHER2, titled Hybrid Atomistic-Continuum Simulations of Boiling Across Scales. And we are all very excited to present this work, coupling LAMMPS and OpenFOAM for multi-scale models. This is the result of a collaboration between Nottingham University, Brunel University, and the EPCC team at the University of Edinburgh. So, quickly going through the outline of this webinar, I will start introducing the reasoning behind why we wanted to have hybrid atomistic continuum simulations of boiling. I will then pass the ball to our collaborator Ed Smith, who will introduce the CPL library used for the coupling. And Gavin will talk about running the CPL library in ARCHER2 with some installation overview and how to use the modules. And then I will be back to present you the coupled OpenFOAM solvers that we have been developing. Ed Smith then will continue going more into the details of LAMMPS and the coupling with the CPL library, and will introduce you the first demonstration case, which is a coupled Couette flow. And finally, Gabriele will take over, presenting you another test case, which is the coupled boiling case, and showing you a demo on how to run this case in the supercomputer ARCHER2. So, why do we want to have hybrid atomistic continuum simulations of boiling? Now, some of you may be aware that boiling flows are an emerging technique for the thermal management of various components, and in particular for high power electronics. Why is that? So boiling flows, they are capable of dissipating very high heat transfer rates thanks to the fact that they are removing heat using the latent heat of the fluid when the fluid changes phase from liquid to vapor. Boiling flows can also maintain uniform surface temperatures because the fluid remains more or less at the saturation temperature during the phase change process. And if you arrange the flow in what we call multi-microchannel evaporators, you can achieve a very high surface to volume ratio so that you have a very compact cooling system. Now, these images here, they're 10 years old, so now we have even more compact systems, but they showcase you how you can arrange the flow into many parallel microchannels, and then if you use a dielectric fluid, you can put the fluid in direct contact with the surface to be cooled down, for example, the CPU of a computer, as you see here in this image, so that you really minimize the thermal resistances to dissipate heat. Now, if we were able to have a microscope, or let's say a big magnification lens, to look at the details down here in the microchannels, if we stay at what we call a continuum scale, CS, so let's say we see the millimeter scale channel, and we see it as a flat wall channel, and we have our, let's say, parabolic laminar flow profile there, and we would see a bubble being generated by the boiling process. But then if we're able to have an even higher magnification lens and go all the way down to the molecular scale, we would actually see that the surface that looked flat is not actually flat, but there are all these nanometer-sized imperfections on the surface, and these are actually those that give rise to the nucleation of a bubble. But as you may be aware, with continuum scale models, for example, based on the Navier-Stokes equations, we cannot really get nucleation. We need a molecular scale solver to get nucleation. At the same time, with a molecular scale solver, we would struggle to capture all the boundary layers that we see at the continuum scale. So that's why we need the coupling of the two methods. So going all the way to the end of our project, this is an example of a simulation where we have a molecular dynamic solver which is actually capable of getting nucleation from first principles. And when the bubble density, let's say when you couple the fields, the bubble is eventually picked up by the CFD solver that continues the simulation solving the Navier-Stokes equations. Now, this is not trivial, of course, and you need a few ingredients to be able to achieve this. You have a continuum scale mesh-based method. You have a molecular scale particle-based method. You need the coupling in between the two to make sure that this happens seamlessly. Now I will stop sharing my screen and pass the ball to my collaborator Ed Smith from Brunel University, who will continue the presentation and will show you how this was achieved.
Well, thank you very much, Mirco. So let me just share my screen. Okay, so the aim of this section is to give you an introduction to CPL Library. So this is the software I've been working on now for over 10 years that's designed in order to link together two bits of software. So the original implementation or application was to couple together two solvers, one being a continuum-based solver and one being a molecular scale solver. So in this talk, we're going to focus mostly on CFD and MD coupling, and we'll move towards the example of boiling towards the end of this session. But the general idea really is to link together any two solvers, and in particular, kind of what would be a grid-based continuum solver with finite volumes, and then some discrete system of molecules. And as Mirco mentioned, the key point here is to really get to that nanoscale detail. So you are really within a paradigm where you're linking two solvers at the same length and time scales. So your MD region is basically providing data, and your CFD exists at the same time and length scales. Now, the anatomy of this is a kind of partial overlap. So what you have here is a CFD grid. You have the bottom CFD boundary condition, and then you have your MD solver that's essentially existing below it, modeling the wall itself. And so what happens here is we then do an averaging process on our molecular system in order to provide that bottom boundary condition to the CFD. So you can see here is essentially an averaging operation. We sum up all of the molecules. This operator here basically says, sorry, 1 second. This operator here essentially says add up the molecular velocity and use that as the bottom boundary condition of the CFD. So in many ways, coupling is really just a way of providing a kind of glorified or more complicated boundary condition to your CFD solver. And so you'll see this in the continuum part. So what we're doing here is with OpenFOAM, we're providing an average of a molecular system in order to give the CFD value. We also have our molecular system driven in order to agree with the continuum solver. So it's a two-way coupling. And the idea here is that we apply some force to our molecular system. So MB is F equals MA. It's just solving individual molecules. And so we're adding some constraint to that system so the two agree. And then typically, just as a bit of the kind of art of doing this, we have a buffer between the two to allow them to kind of relax into each other. Okay, so before we get into the kind of details of that, and we'll talk about that in the appropriate sections, I want to talk just a bit about the kind of software itself. So CPL Library is a library. So it's a shared library that basically provides a minimum set of commands to allow you to do coupling. So the minimum set of commands are an initialize, a setup, and then a send and receive. So there are a variety of other commands, but the idea here is that it allows both codes to kind of link together with just a minimum set of commands. So it's really designed just to facilitate the exchange of information on a supercomputer in an efficient way. And the idea here is that both codes are then completely separated. And so the only point of contact they have is really this process of initializing and setting up, and then all of the information between them is sent and received. And both codes remain completely separate, completely independent, and then the only thing you have to do is link in this shared library. Now, we had a couple of people asking before about granular mechanics, and this is something we've looked at. It turns out granular mechanics as a problem is basically just a special case of this setup. So rather than having kind of partial overlap between the domains completely overlap, and then your force of constraint is some drag force between the molecules. In this case, the molecules are particles of sand, for example, or dirt. And then you have some assumption that your particles are smaller than the cell, and you do some averaging. Now, I'm not going to talk more about granular mechanics, but it is an application we've done some work on. So why did we decide on this particular design philosophy for Coupler Library? It's really based on the idea from MPI that, within MPI you have a standardization of communication where each individual process runs independently, and then they can send and receive information between each other. So you very explicitly say, I want to send information from one code to another, and you call MPI send and MPI receive. Now, if you have a Cartesian coordinate system, so this is true in any kind of CFD or MD code, you're dividing your domain up into a set of individual processes, it's useful to create a Cartesian communicator with MPI. And so what this does is it essentially splits your domain up into a series of processes that each have their own part of the domain. So you're solving the grid or the individual molecules on part of the domain. And so this Cartesian communicator is really the building block of a coupled case. And just to give you an example of that, a Cartesian you'd create would be, say, 8 by 4 by 4. And the advantage of using this Cartesian coordinate communicator with MPI is that it allows this reorder flag, so you can optimize the topology itself and based on the kind of node proximity on the supercomputer. And then you can get the adjacent processes and work out where to send information using MPI cart shift and other commands. So it's kind of helper function that lets you set up the topology of your system. Now, one thing just to mention before that, communicators are used to determine which processes can communicate with each other. Now, send command, you can see you pass in, say, an MPI com here. Now, by default, all communicators exist on what's called an MPI com world. But the problem is when you do coupling that both codes think they're the only code in the world. So both LAMMPS and OpenFOAM have and use MPI com world. Now, what you see recently is there's been a move, and actually both codes have actually developed in the later versions not to have this being true anymore. But one of the ways we solve this problem is you can either run it as a shared paradigm where you have both codes running within what's called an MPMD setup, or what we call a shared paradigm where you have a colon between them. And in this example, you have to actually patch both codes to replace MPI com world with some local communicator to allow them both to not do blocking communicators on the world com. The other way we solve this, and this is something that has only recently become available as ARCHER2 has just gone through a software update, is you actually create both codes with their own MPI com worlds and you merge them together using the MPI port system. And if you do that, you don't have to patch both codes. And so this is something that allows a much more elegant form of coupling. So how does Coupler Library work? Well, essentially what we do is we basically link the Cartesian grids between both codes. So this schematic shows how that works. Your MPI initialize and MPI cart create would create a kind of grid of processes. So these aren't CFD cells. Each of these is a process. So you've got 16, so 4 by 4 processes in the MD code and 2 by 2 on the CFD code. When you talk coupler initialize, what that does is it creates a single shared communicator in the way I've just discussed. So either by linking them together as two parts of the same MPI com world, splitting that communicator, or merging together two separate codes using MPI port system and create a single communicator that allows them to communicate with each other. Coupler setup, we pass in the Cartesian coordinator, the MPI Cartesian communicators of both codes. And what that does is it sets up a mapping between the different parts of the domain that overlap. So in this example, they're completely overlapping. And so the kind of pink regions are overlapping with these regions. The green is overlapping with the green. And what that means is when you go to call couple send and couple receive, all of the communication is handled automatically for you. And so these are the kind of key steps. You'll set up a shared communicator, you set up the mapping between those, and then in your code, it becomes as simple as calling send and receive. Just to mention, the scaling using this process is pretty good. We originally designed it for scaling and then have tried to make it more usable. And up to about 10,000 cores, we see pretty good scaling. And just to mention, this example is very much a kind of low compute example. And so it's quite a tough test of the actual code. And so I think in practice, you'd actually see better efficiency in that scaling. Okay, so just a quick mention of how you build coupler library. In principle, it's Linux-based shared library, and you essentially would call something like make platform GCC if you're doing it locally, or on platform Archer on ARCHER2. The coupler library itself is actually very, very simple, very minimal. It's just a Fortran source code with C++ and Python wrapper, and a set of utilities to help you couple. But the prerequisites are Fortran compiler, C++ compiler, Python, and MPI. So that's all you need for it. It's a pretty minimal set of requirements, MPI being the hardest one, but always available on a supercomputer. And the two key files here are the methods and modules on the right-hand side. If you want to do more complicated things with Python, you need a wider range of modules, and there is actually a module available on Archer. If you have a look at this guide here on the Coupler Library website, which Gavin will talk a bit more about, that has all of the instructions for how to use it with the module system on Archer. Okay, so just to show how this works, we have the kind of Fortran core with the various wrappers around it, and then a wider set of utilities that allow you to do coupling. So the idea is the core code is literally just the coupler send and receive and the initialize and setup, and then everything else around that facilitates the coupling. And the nice thing about that is it allows us to kind of test the individual bits. So the core itself can be tested with a kind of range of different topologies. We can make sure that the core functionality of send and receive are working correctly. And we can also then do a range of different Google tests on the individual utilities that do the kind of forcing and field type operations I'll talk more about later. The idea of doing that is then we get this division of concern. So coupler library can be tested by itself and just make sure that scales appropriately and it does the right kind of communications. And then what you can start to do is actually do coupling to kind of minimal scripts. So this comes to the software concept of mocking, where you mock, say, a CFD code and link it to an MD code and check that it works as expected. And I'll talk a lot more about how we do that in the second part of my on the Couette flow example. But here are a couple of examples. So you can see we do a kind of mock test with CFD, a mock test with MD. And so both have been tested independently, and then we bring them together at the end. So it allows a kind of systematic debugging of the code. And then all of this is automated on GitHub Actions. And so the idea here is that we go through all of these permutations every time we make a change to the source code. Okay, so just very briefly, this is a minimum mock code. I just want to highlight really here how minimal the code is to get a kind of coupled example. You initialize here, you set up the CFD. Now note that you've got the number of cells specified here and the kind of processor topology specified here. You then essentially do a send receive operation and a send operation. And so this is kind of a dummy example where you can see here's the kind of MPI Cartesian grid. These are the cells specified. And then the mapping here essentially means that those send and receive operations go to the right set of processors on the other side. And there's examples for Python and C++, and Fortran and C++. Don't worry too much about reading these. The key point here is just that these send and receives go between the two codes, and they are all basically the same format, just in different languages. And you can see the form of the coupler setup and initialize are pretty similar in all three languages. In terms of running, if you want to run, you need to make sure you source if you do it locally or load the module. This is most common cause of errors. Just make sure you've done that. It's because we don't install it in a central location. You then need to compile the code linking explicitly into this coupler library. And so CPL F90 or CPL C++ are helper functions to do that, or you can link the shared library manually. And then you need to either run it in shared mode with this semicolon. So that's the CFD and MD together. Or you open them in two separate terminals, you run them separately, and they merge together using that port linking system. In Gavin's examples, he'll talk about how you do that with the run script on Archer. And there's also another helper function in Python that lets you do that. So I'm aware of time now. I think I'm pretty... So a couple more minutes just to this. So the other thing just to mention is the coupler input system. This is how we specify how the two overlap. So you have your CFD code, you have your MD code. The coupler input is an input file that essentially you specify using kind of keyword inputs. The two codes overlap. And so this is done purely in terms of cells. There is only one grid assumed in both codes. It's the CFD grid, which is the same as the coupler grid for simplicity. And then you literally just specify how many cells overlap. And so this is just to really simplify the kind of topology of setup. And so in this case, we're saying just 3 cells are going to overlap here. And so you just specify that in the overlap extents. We're saying the full overlap of 16 cells in X and 1 to 16 in Z. And so then you specify the overlap region, and then you can specify where the constraint is applied. So we're specifying that cell 3 of the overlap region, and the boundary extents we specify as cell 1. And there's a subtlety here, which I'll come back to in the LAMMPS section, where depending on whether you want to average above or below that plane, or at the midplane between the two, you might want to tweak that. But this is something that's handled within LAMMPS itself. Just to help you set up the topology, there's a small tool that's located in Coupler Library Utils Design Topology. You do need WX-Python to run it, but this essentially lets you kind of check out the different topologies, and then you can run those two, and it sends a kind of sine wave just to check whether or not it's doing the right thing. And so this is an example where we've gone from, say, one topology to two processes topology, and you can see and make sure that this kind of sending and exchanging works as expected. So the last thing to mention is just there's a couple of other bits of software, one for plotting, which is PyDataView, and one that helps with some of the testing called SimRaplib, that are used as part of the kind of wider software stack of these. If you want to use PyDataView, and one of the examples we'll use that later on, you can literally just git clone that, and it's based on Python. You don't need WX-Python in order just to do the basic plots. And just to mention, this is a research code. Generally speaking, we only support the case where there's just overlap in Y and complete overlap in X and Z. We've not really had anyone need anything else, and it's not something we've needed ourselves internally. There is a testing framework, so hopefully if we wanted to extend it, it would be possible. But generally speaking, stick to that topology where X and Z completely overlap. We tried to put error messages to stop that happening, but really that kind of overlap case is the one we support. And recently the deployment on Archer means it should be very easy to use that, but please feedback any issues and any pull requests. If you want to develop new cases, that would be really appreciated. It's all open source software. Okay, brilliant. So just to summarize, we're coupling two codes together, CFD and MD. They're built separately, and then they link together as a shared library into both codes with a minimum set of commands. So you're making a minimum set of changes within your codes. And this is good because it allows you to test both codes independently and keep them tracking the latest repository version. It maintains the scope of both codes, and it also promotes optimal scaling because all exchange is kind of point to point. So with that, I'll stop and I'll hand over to Gavin next.
Yes, thanks, Ed. Okay. So this is a very short presentation, only 10 slides. This is an overview of what I'm going to talk about. It's very brief, and I shall describe an overview of commands required to install Coupler Library onto ARCHER2, along with how to install some examples of how to couple OpenFOAM and LAMMPS. Then I'll go on to describe how we can replace this 30 lines with just 4 lines by using the ARCHER2 module system to access a centrally installed version. I'll describe how to run a very simple coupling of 2 basic applications, and then move on to how to couple an OpenFOAM simulation with a small dummy molecular dynamic application. And then finally, just a very brief description of how to run 2 parallel applications, each with their own distinct MPI communicator, rather than just one single MPI communicator. So here, so to install a Coupler library, we run these 4 module commands. We employ openfoam.com version 2.106 in our example. The load ggcc is to replace the default GCC version 11 that comes with OpenFOAM. It wasn't compatible with one of our applications. The Cray FFTW module is not strictly required for the Coupler library, but it is required for the LAMMPS installation later on, so we might as well use it from the get-go. Thereafter, we have to clone the repositories and install them. So here we are cloning the Git library, and then installing it. Of course, here I'm using my own project, which is Y23, and my own username, Gavin CPL, so replace it with your project and your username. The next stage is to then clone the OpenFOAM example Git repository and install that. The source.me.sh line, that source.me.sh file is different from the previous source.me.sh. The soft link updates the CPL pstream directory to be dependent on the underlying OpenFOAM version. Here, as I said, it's version 2.106. And then the OpenFOAM uses a library called pstream, which in turn uses the MPI library. So what we do here is we make our own pstream version, which builds the CPL version of pstream, and that supersedes the OpenFOAM version. And then the other make statements, test foam, test socket foam, interfoam, and interfoam hard T phase change are all examples of increasing complexity that can be used to base your own coupled applications on. The final stage, if to install it yourself, is to clone the LAMMPS Git repository, which is very similar to the OpenFOAM. Here, of course, we're downloading our own. We're downloading the most stable, most recent version of LAMMPS, and once again, the source.me.sh file is different from the previous two. So this can be all avoided if you want an easier life and just use the module system from ARCHER2. Only 4 lines will get you the same setup, although you can change the input files, but you're unable to change the source files or the executables. So the first line there is to module load other software. That's required because our modules are supported by ourselves rather than by the ARCHER2 team. And the link at the bottom will give you a very long, was it 25 pages, a user guide of how to use all the examples available, either through modules or through your own installation. So this is what, to run a coupled application, or using an MD app and a CFD app. This is all you need using the module. So you have the 3 module commands I mentioned before, plus that source term on the OpenFOAM library. If you're an OpenFOAM user, you'll be familiar with sourcing something to set up the local configuration. And then when all that has to do is then just couple the example, compile up the 2 codes, and then submit the batch script. I'll show in a second. I think some important things to notice here is the copy line has a full stop at the end. That's often missed as an error. If you're using a self-install rather than the modules, then the environment will look a little bit different. So the modules will be different, and the copy line is not required, of course, because you have it installed yourself. So this is what the batch script looks like. This is, as I mentioned, this is a shared MPI communicator. What's to note here? The module couple LAMMPS isn't strictly necessary for this example because we're only looking at the couple OpenFOAM code module, sorry. But it's good to have it there anyway because we're going to be using LAMMPS in the future. If it's a self-install, again, the environment will be different, and yeah. So here's an example of switching out with the dummy OpenFOAM with an actual OpenFOAM simulation, and hopefully it'll show just how easy it is to do. The copy line is slightly different. It's just the location of the example, and the directory is the same. We're compiling a small code there and submitting. The executable for the OpenFOAM is provided. It's already in your path. And here's the same batch script, but this is the only changes you have to make to go from a dummy case to an actual OpenFOAM simulation. So you're running block mesh, decompose par, of course. And there you're replacing the CFD dummy with the name of the executable. Here we're running 2 parallel applications. Both are running 2 threads. Each application requires its own node on ARCHER2, and that's the case whether you're running shared or distinct communicators. The shared ARGS environment I should have mentioned earlier, that's used to pin MPI tasks to cores. And then my final slide is the differences between running shared communicators and distinct communicators. So both are available using coupler on ARCHER2. The availability on ARCHER2 is quite recent. That was a collaboration between ourselves in Cray. So that's now available. That involves using MPI port, but that's all under the hood. So coupling codes in ARCHER2, they're referred to as multiple heterogeneous jobs in the documentation. And as I said before, each job requires its own, at least one node each. And they reside in what's called, in SLAM terminology, the batch script manager terminology, as a het group. Distinct communicators are actually called the client-server model. And there's the URL for the full description of how to run couple codes on ARCHER2. So with that, we can answer some questions at the end. But for now, I think I'm passing on to Mirco.
Yes, Gavin, thank you very much. So I'm back on the stage, and I will continue with my presentation. So this is where we left before. So you got an introduction from Gavin and Ed about the principle of the CPL and the coupling. Now with my next few minutes, I want to show you how the coupling is seen from the OpenFOAM side, so from the continuum solver side. So we have mainly modified a couple of existing solvers in OpenFOAM. The first one I'm going to show you is the solver that we have renamed CPL IcoFOAM. So IcoFOAM is probably one of the most popular solvers of OpenFOAM. It's a transient solver for incompressible laminar flow of Newtonian fluids, and in the case of CPL IcoFOAM, it uses the CPL coupling to set some of the boundary conditions. So IcoFOAM is solving the continuity equation for an incompressible flow and the momentum equation for a laminar flow of a Newtonian fluid, which appears in the following form. And let's take, for example, one of the cases that Ed Smith will show you later on, where we have a Couette flow, where we have the OpenFOAM region meshed with a structured regular mesh here. On the top, we want to impose a fixed horizontal velocity to the top boundary. And the bottom region of the domain, we want it to be solved by an external solver, for example, a molecular dynamics solver. So what happens is that OpenFOAM will get information about the boundary condition to be set at the bottom boundary as a Dirichlet boundary condition from the molecular dynamics. So as I will show you now in the source code, OpenFOAM will get the initial conditions and the boundary conditions at that boundary from the coupled solver. So in the case of the Couette flow example, the bottom boundary will have 0 velocity, so it will be a stationary wall. So if now we are going to plot the horizontal speed as a function of the vertical coordinate, what we are expecting is that starting from a 0 velocity field everywhere, we are expecting the velocity field to converge towards a linearly increasing velocity as time goes by and become completely linear asymptotically as time goes to plus infinite. So what are the modifications we have done to the original IcoFOAM.c solver in OpenFOAM? So this is a snapshot of our modified IcoFOAM solver, and in the red box you see the changes we have introduced. We have an include CPL socket form.h, which links to a specific library to make OpenFOAM communicate with the CPL. And then within the main region of the solver, we have another box here where the solver is going to verify if this is a coupled case or not. And if it's a coupled case, it will initialize the communications. Now, all the solvers we have modified, they're modified in such a way to be very easy to read. So you will see all these boxes coming all the time in our solvers because everything is handled by these nicely organized libraries so that it doesn't mess up the code here. As we scroll down in the solver, we see now that if this is a coupled code, there will be the initialization of the CFD field, and there will be a first send command that will take the fields from OpenFOAM and will send them to molecular dynamics, and a receive command here where OpenFOAM will unpack velocity and send them out. This is still for the initialization of the fields. Later on, during the temporal loop, here we start with the packing of the information received from the CPL, and then here we have OpenFOAM again communicating with the CPL library. This is done at every time step so that the coupling between OpenFOAM and the external solver is completely done both for the input and the output fields. After this, IcoFOAM continues as usual by starting, for example, the solution of the momentum equation with the predictor step. So from now on, the solver should be as you are used to see it. Next, I want to introduce you the actual boiling solver that we have used, which is CPL interFOAM hard phase change. The starting point of this solver is OpenFOAM's interFOAM solver. InterFOAM is a solver for two incompressible immiscible fluids using a volume of fluid phase fraction method based on an interface capturing approach. We have added Hart and Vondra model for phase change, whose details are all available in these publications down here. So for those of you who are not familiar with the volume of fluid method, the volume of fluid method maps the domain giving 1 to the cells which are filled with the fluid 1, 0 to the cells that are filled with the fluid 2, and we have values of the volume fraction in between for cells that are partially filled by one fluid and the other one. The equations that the solver is solving are the continuity equation, volume fraction equation, momentum equation, energy equation. And these equations are augmented with these source terms that introduce the phase change of the interface. So all the red rho dot are the phase change at the interface. And how is this calculated in the solver? The rho dot is calculated proportional to the norm of the gradient of alpha, which represents how much interface area you have in the cell, times JE, where JE is the interfacial mass transfer. The interfacial mass transfer for the case of boiling, for the case of evaporation, is calculated as proportional to the interfacial superheat. And the constant of proportionality is this ratio of interfacial heat transfer coefficient and latent heat. The interfacial heat transfer coefficient in the current version of the solver depends on the accommodation coefficient gamma, the molecular mass of the fluid, universal gas constant, density of the vapor, latent heat, and saturation temperature. These are all constant for the time being. All the details are in references 1 and 2. So the coupling then, as you can imagine, OpenFOAM needs to know velocity, density, phase fraction, and temperature at the coupled boundary. These must come from the molecular dynamics solver in our case. And we're going to see next how this is achieved in the structure of the solver. But as you can imagine, the structure of the solver is very, very similar to the one you have seen for CPL IcoFOAM, because we are going to introduce the extra bit for the coupling in the same exact way. So again, we see here inclusion of CPL socket foam.h, an initialization of the communications in the red box here, exactly the same as the CPL IcoFOAM. Scrolling down the solver, we have again the initialization of the fields that will be received from molecular dynamics and sent to the molecular dynamics solver. And then within each temporal time step, the solver will send information from the CFD to the molecular dynamics via the CPL, and at the same time receive information for velocity, phase fraction, density, and temperature. And this is pretty much all. So all the solvers, they will just look exactly the same. The only thing that changes between one solver and the other is the amount of fields that are exchanged, which depend on the kind of equations that are solved by the specific solver. So this is all from my side, and I'm going to pass the ball back to Ed Smith.
Thanks, Mirco. So, one second. So that's the OpenFOAM side. And so now I'm going to talk to you about the LAMMPS part of the coupling. So in preparing this webinar, we kind of assumed that more people would probably be on the CFD and OpenFOAM side and be interested in LAMMPS. So I'm just going to give you a quick overview of molecular dynamics. So MD is basically just solving Newton's law for individual discrete molecules. You get the positions by integrating the accelerations to get the velocities and the velocities to get the positions. And then you calculate the accelerations by using Newton's law. So you're adding up the forces on that molecule from its interaction with all other molecules. And so it's this kind of process of working out the interaction in an n-body system and using that to integrate your molecular position. And you loop through and do that for all n molecules. So the reason why this is attractive is because, you know, your only empiricism, your only assumption in the process is that the intermolecular potential comes from quantum mechanics. Now, in everything that's presented here, it's the simplified Lennard-Jones potential, but you can replace this with whatever form of intermolecular potential you want. So we can get kind of things like phase change, and we can get all sorts of wall interactions a priori from just this kind of calculation of the intermolecular interactions from there. Now, this is actually a subset of molecular dynamics called non-equilibrium molecular dynamics, and the non-equilibrium comes from the fact that we're outside thermodynamic equilibrium. So anyone who does fluid dynamics, this is what I would call molecular fluid dynamics, but the key point here is we have temperature gradients, we have fluid flows. So these are things like Couette flow, that's sheared wall-bounded flow, or Poisson flow, which is the kind of pressure gradient or gravity-driven flows. So you also potentially have temperature gradients, and so these are enforced using things like thermostats, the Nose-Hoover thermostat, or if you want to build walls into your system, you can tether them to sort of harmonic or anharmonic lattice sites, and then you can slide those lattice sites in order to kind of move the walls. And this allows you to kind of create all of the kind of moving boundary conditions, remove heat, add heat, as you need to enforce the kind of typical fluid dynamics type problems. And there are a whole range of other techniques. We've actually got a special interest group. If anyone is interested in finding out more, who's on the kind of fluid side, please go to this, sign up. We're probably going to organise another meeting next summer. Okay, so the package we're going to use is LAMMPS. This is arguably the most popular molecular dynamics solver. It's popular because it's very extensible. So it's developed actively by Sandia National Lab, and they've got a very good community. There's people there working full time on it. Written in C++ and designed to be highly extensible. So it's made of a variety of different packages. But what's important here is that you can basically turn them on and off. And most of these packages are written by users. So you can say make PS and see which packages are currently included in your LAMMPS build, and then you could say turn on a package that does long range interactions, for example, or granular mechanics or Brownian motions, and then you make the code again with those packages built in, and so people can add those packages. The next thing to mention is the LAMMPS input format. So you essentially create your systems using a pretty almost programming-like interface through an input system. The couple of things just to mention in a typical domain setup, you specify, say, the FCC lattice. So this is saying that I want, say, 12 lattice units in X, 24 in Y, and then you specify, say, how wide your wall would be. You'd also have a keyword for how many processors you've got, and then you would create essentially a lattice of FCC molecules, and you create your simulation box to be filled with that uniform lattice. And so what this means is your physical domain size is then created indirectly as a result of the number of lattice sites. And so you need to actually get that for a coupling problem. We'll come back to that in a bit. The other thing just to mention is in order to do kind of non-equilibrium MD, the most important thing is probably tethered molecules. And the way we do that in the examples we provided with CPL Library is to kind of set particular sites to be tethering sites. So we create kind of virtual molecules, and then we essentially use a bond coefficient between real molecules and these kind of fictional molecules. So these fictional molecules are turned, all of the interactions between them and the other molecules in the system are turned off, and then we create a bond between those molecules. So I mention this just because one of the questions I've had a few times are people trying to work out how you actually, do the non-equilibrium MD thing. So this is kind of one of the tricks to do that. Okay, so then these walls here now are kind of a set of tethered molecules held in place, and we've got this kind of coupling overview where we split our two codes off. And the only thing that's kind of needs to be added into the LAMP side are these initialize, setup, and send and receive commands. And those send and receive commands send the information that can be used in order to apply. If you remember, we had to have the averaging process in order to get the MD CFD boundary conditions. So that's going to be some summing process over some MD region to add up the velocities of the molecules, or momentum in this case. And then you want to have some way of applying a force, and that force of constraint is going to be based on some CFD field value that means the two will agree with each other. Okay, so that's our kind of aim within the actual LAMPS package. And this is why this division of kind of concerns is quite useful, because from our LAMPS point of view, we now just need to work out how we can get those quantities. The reason why LAMPS is so popular and has got so many packages, I think the majority of the code is actually user contributions, is because it has what's called a hook system, where you can drop in code wherever you like within the overall LAMPS codes. This is a kind of single loop through. So going sort of down here, and then it continues down here. And you can see a kind of each time step, it's kind of calculating the force and then evolving forward in time. And so what you can do is you can just write your own fix that say goes pre-force or end of step or wherever you want within the overall LAMPS code. And so we wrote a user CPL package that you can turn on using this make yes user CPL, and then you use make CPL with them, which basically builds it with the CPL library linked in. So what you get as a result of that is a version of LAMPS that has CPL involved in it. And so what user CPL includes is a couple of new fixes, a fix for applying the forces, and a fix for initializing and setting up the coupled run within LAMPS. And then most of the common code is bundled in this coupler source socket LAMPS. And all of this is on GitHub. I'll give you the URLs in the next part. So the process of actually installing this, because it's not part of the core LAMPS packages, at least not now, is you actually have to build it. We have an app to do that. And so this app you can essentially download from GitHub. You have to just specify in a file called code installation directory the location of your LAMPS directory that you want to patch. And then if you decide you want to do the shared paradigm, so that's the one where you need to patch MPICon world, then you need to do an extra step where you patch the LAMPS code. And then after that, you do the make command and it will patch the code for you. You can include some packages if you want to, and then build the whole thing together. And you can see detailed documentation of this on the website. Alternatively, you can just use the version pre-bundled on Archer, but I'm including these kind of steps just to explain for people who want to kind of set up locally. So once it's built, you can essentially then include this fix. So this is a new fix called fix CPL fix. So there's a couple of keywords I just want to focus on. We have the force type keyword and the send type keyword. Okay, so this essentially determines the two key components of a coupled simulation. So if you remember our picture here, so the force type is basically the force we're going to apply to our top of our MD domain to make it agree with the continuum. The send type is essentially the averaging process in order to get those values there. So the force type you can choose between velocity and stress. There's also a whole bunch of granular flows. If anyone's interested in that, I can talk more. And it's designed to be easily extensible. And so on the website, the CPL Library website, we've got a whole series of techniques for extending and adding your own forces. And there are a bunch of different keywords you can add in, depending on whether you want to overlap or interpolate and various kind of tunings. So the two coupling forces that we support are broadly divided within the community of coupling into state coupling and flux coupling. These are the simplest forms of them. So the velocity coupling is basically just the current difference between the MD velocity and the CFD velocity is applied as a constraint force. So for people working as engineers, this is a proportional constraint that is just based on the difference between the two simulations. The other type of coupling is stress coupling. And so this essentially takes the CFD state of stress, which is calculated from your CFD stress tensor. That would be a function of, say, viscosity and pressure, or more complicated cases, maybe some viscoelastic relationship, and applies that directly as a force. So it's dot normal and then multiplied by some weighting function. And so both of those forms of coupling are available. Okay, and then in terms of the send type, so the averages you can provide back to the CFD code, you can choose whether you want to do n-bin, so that's the density within the system, the velocity within the system, or momentum, or you can calculate the stresses and send those stresses to the CFD code. And generally speaking, most of the time we want to do the velocities and the number of bins, and so that's what we call a mixed type, and there's these kind of shorthand versions defined. If you want to develop new ones, as I mentioned, there's a kind of tutorial on the website. Okay, so just a summary for this part, LAMMPS is a powerful MD tool. We can add packages, which we have done here, the user's CPL for coupling. In order to allow you to build that, you need to use the user's app LAMMPS, and that contains essentially a script that will build everything for you, provided you just point it at whichever version of LAMMPS you want to build it for. And it will put the LAMMPS LMP_CPL into the binaries for you to be able to use. But these are also available pre-built on Archer if you load the LAMMPS CPL module. Now, in order to set up a coupled run, you just add the single keyword. If you take this keyword out, it's uncoupled. If you add this keyword in, it's coupled. And then you can choose between which force type you want to apply. So that's velocities, and whether you want to average velocities and send them back. And it should be easy to extend. The other thing to mention is the coupler input file will also be needed, and that will be discussed in more detail in the next section. Okay, so this is the kind of final part of the talk where I'm going to show you a kind of complete coupled Couette flow example. The full example code is available here under the CPL Library GitHub, and then you need to have both the LAMMPS and OpenFOAM app installed. If you decide you want to run this on Archer, this is literally 4 lines of kind of module loading. If you want to do it yourself, it's slightly more involved, but the most complicated step is building OpenFOAM itself, and we support version 2.106 at the moment. But it should be possible to extend to other versions. Okay, so we're going to look at the coupled case. This is coming back to this picture of the kind of finite volume solver linked to a discrete system. So essentially, we're going to take that system and we're going to apply a force type at the top of our MD domain, and we're going to average our CFD domain and apply as a boundary condition. And in doing that, we'll get Couette flow. So the black line here are the analytical solutions. The red are the CFD values. We're applying a kind of top boundary condition with a value of 1 that's driving the flow. You can see this blue part here is where the constraints apply to our MD system. So we're applying a force along this part of our MD domain that's kind of driving the molecules along. And as a result, there's a kind of fluid flow induced. And that fluid flow then essentially moves the molecules here by a kind of lesser amount. And that is then averaged and provided back as a boundary condition to the CFD. And so both systems evolve together as if they're a single system. And so this is why it's a particularly nice example to look at, because it has to have the two-way coupling for it to work. We also know the analytical solution that it should agree with, provided your systems are big enough and you've kind of taken into account a kind of partial slip near the boundary we see with MD. It also allows you to look at kind of more interesting cases, right? So we could look at, say, rough walls within the molecular system. We could look at textured surfaces like posts. We could look at, for tribology applications, polymer brushes, and they've been researched for kind of drag reduction. And, you know, this would allow you to, say, design different chemical species and look at how they affect and improve the flow. And in particular, we can actually push the system sizes with this type of coupling to get a kind of coupled, a turbulent OpenFOAM simulation and a molecular region near the wall where your kind of near wall region, this surface texturing could be explored to see how it affects turbulent flow. So that could be for surface texturing, it could be kind of a different chemical coatings and things like that as part of a kind of turbulent. This is the minimum channel example, so it's a small turbulent box, but it's one of the kind of applications. Okay, so before we go into this, let me just make a note on numerics. So generally, anyone who's worked with CFD knows that numerical blow up in CFD is a big problem. The simplest check is CFL, which is obviously just a linear check, and there's lots of non-linear problems. But, you know, essentially, you know, you've always got this problem of blow up within CFD, and you know, it's kind of difficult to get kind of stable solutions. And although OpenFOAM is pretty stable, it's very difficult to debug if you suddenly get an instability. And the reason for that is because it could be an error in the coupling exchange. So you could have made a mistake and sent the wrong thing, for example, or set up your case incorrectly. But you could also have a situation where your MD code hasn't been averaged sufficiently and you've actually got too much noise, or maybe your overlap region is too small. And so what you've got is a kind of feedback loop. Or it could actually just be that your OpenFOAM solver has too fine a grid and so CFL is violated, or you've maybe got non-linear instability. And so actually debugging this kind of addition of two non-linear dynamical systems coupled together and working out which one is actually causing problems is extremely difficult. And so we suggest building up your case using mocks, which is what I'm going to talk about today. So this is the process. We essentially, step 0 is to kind of couple together two minimal mock codes. And these are the ones that Gavin talked about how to set up on Archer. You then swap out one of those mocks for OpenFOAM, using OpenFOAM with exactly the same setup as the mock. You then swap out on the other side, you do the minimal CFD case and you link it to LAMMPS. And then finally, you can couple both together, knowing that you've checked out. And each of these steps essentially gets rid of some of the errors. I'm just going to talk about that process. So first of all, we check the geometry, process topology, and visualize. And so just to mention that LAMMPS setup is in FCC units, and so the physical domain size is something you actually have to run LAMMPS to see. So this would be a kind of domain 16.7 by about 45 by about 16.7. And so there's a kind of minimal applet you can try this out with and just check that it works. You can run it to make sure that the output's correct. And so you do these minimal scripts first of all with the correct geometry and setup that you want to do for your main problem. And you can check these kind of outputs look okay. You can also do it kind of at the lower level. So you set up a minimal MD with the right sort of, size of domain, the right processor topology you want. You'd set up your overlap size to be correct in coupler input. So that's 1 and 4. So that's an overlap of 4 cells. Where cell 3 is the one that you're constraining and cell 1 is the one you're averaging. And so you can see it looks something like this. And you can check, using dummy send and receives that the right values are being sent backwards and forwards. So once you're happy that works as expected, you then swap out your minimal CFD code for OpenFOAM. And so what you need to do is set up OpenFOAM to match the same properties as your minimal CFD code. So just to kind of quickly go through the different things you need to set up. So the bottom boundary condition just has to be set to couple receive MD. And the send type is actually the version that's sent from LAMMPS. So nothing else needs to be done with this. This is just make sure your bottom boundary is set to the right value. The exchange is handled internally by CPL Library for you. You need to make sure your grid is set up to the right value. So this will be under polymesh. For uniform grid, you just want to make sure it's the same size. In this example, we're doing 8 by 8 by 8. And you want to make sure your processor topology is the same as your minimal MD code. And so we're just doing that setup there. So once all three of these different values are set up, and notice your coupler receive is set in both the initial velocity fields as well as in the block mesh dict. You can check that works as expected, and so you can swap out the minimal CFD for that minimal for the OpenFOAM case. And then this allows us to actually test Couette flow example, but driven by the minimal script. And so what we do is we actually specify our boundary condition. So our minimal MD Python code is now essentially driving the boundary condition for OpenFOAM. And so we can try different boundary conditions and we can check the response agrees with Couette flow analytical solution. And so this is one of the tests that's automated as part of the debugging of this particular case. You send some test value and you test that value is doing what you'd expect it to do. And so this is why it's called a mock. It's essentially a mock version of the kind of LAMMPS code. Okay, so now when we've got that working, we go on and do the same thing on the LAMMPS side, and we couple LAMMPS to a minimum CFD code. So the LAMMPS example is the one we talked about before, but instead now we're just sort of lopping off the top and solving Couette flow without a top. We're setting up the tethered molecules as before and the domain size, and then we're adding this fixed coupler fix into the code with a force type and send type. And so this force type will essentially apply this velocity to this region in space. The send type will average the kind of bottom boundary condition there. And then notice this boundary average, we specify that we want the region below to be a value we get. And so then we can apply different forces and we can compare the received value to the analytical solution. And again, this is good for checking mistakes and making sure that you're actually receiving back the cell you think you are, make sure your applied force is working as expected. And it again allows you to kind of decompose the problem into two simple parts. And again, we can test that against the analytical solution for Couette flow. And then finally, once we've got all of that working, we bring together the two and we run with OpenFOAM and LAMMPS. And so in order to do that, this is the set of commands that we need to run. On the right-hand side is a kind of terminal session Archer where I just showed how that works. So we log into Archer. We have to load other software that allows, as Gavin mentioned, the actual packages we built separately from the main Archer set of modules. You load coupler OpenFOAM. You have to source in Foam Coupler app to get the right environment. So we do that. You can see I'm copying over the commands here. So the first command here is loading the other software, and you can see it tells you that you're using non-ARCHER2 softwares. And we load OpenFOAM, and you can see the usual sourcing of bash RC in OpenFOAM appears. And then now here we're basically going to copy over the example. So you go to your work directory. I'm going to do it in the work directory. This just basically takes your home path and puts it as a work directory, and you can see we're in work, and then this is my username. And then we're going to copy across the example of LAMMPS OpenFOAM, go into that directory, and you can see inside that directory we have all of the files. So this is the LAMMPS directory, the OpenFOAM input file, the LAMMPS input file here, and then we submit the Archer batch file here. And so if we do that as sbatch, you'll see that I get an invalid account combination. If we look at the actual Archer file, you can see it's because my account is still specified to Gavin's version of that account. So that would be the thing you change to whichever code you've got on Archer. Then you can just submit this case, and it should run probably within a few minutes. Okay, so then in order to analyze it, we can do that using Python. In order to do that, we have to start a virtual environment, but you can just copy each of these commands. You have to activate a virtual environment, install matplotlib, as well as PyQt5, just to have the right backend to be able to view that. We also clone PyDataView, which is just a visualizer. You then have to just edit plot coupled to basically just specify where the location of this PyDataView directory is, so that it knows where to load all the plotting scripts. And then you run plot coupled, and you can see we get essentially the coupled case. So the blue points are LAMMPS values, the green points are CFD, and the black lines are the analytical solution. So you can see it's not a great agreement here, and it's because we've got a very, very small MD case. This is a really kind of minimal dummy, sorry, poor choice of words, but it's a minimal MD example, so quite a small case. If you go to bigger cases, you'll get closer to the kind of agreement we've got here in this, which is a much, much bigger simulation case. Okay, so that's it for this part. I've talked about unsteady Couette flow is the canonical test case for coupling. It's nice because it's wall driven and we have an analytical solution for it, and you can drive either side of it. It requires two-way coupling to be working in order to get the correct agreement, and that's a correct agreement with the analytical solution. And so I've shown this way of working where we start from two mock or dummy scripts to get the geometry, and then we gradually build up in complexity with the dummy and OpenFOAM, then LAMMPS and dummy, and then finally putting the two together. And in doing that, you eliminate the kind of potential sources of error along the way. And the other thing about this is, as you're going along, you can basically build up tests that test individually. So those individual mock codes can actually be used as part of your testing process. You can automate, an insertion of a particular value and check whether the response of, say, the OpenFOAM code works as expected. So, for example, for a given boundary condition, you would expect one time step to do what you expect. You could build a test into your testing framework to do that. Okay, so that's it for me. So now finally we're going to move on to a full comprehensive example using boiling. And so I hand over to Gabriele for that.
Thanks, Ed. I'll share my screen first. Right, so good afternoon, everybody. In this presentation, I'm going to show you how to actually run a couple of MD CFD simulation to model nucleate boiling. So this is the outline of today's presentation. So I'll show you how a quick description of the problem along with the setup of the case, and we will have a look at the main files that a user needs to edit in order to run this case. There will also be a recorded demo on how to run this example on ARCHER2, and finally quick discussions on some of the results. So we want to model a nucleating bubble in a heated cavity. So if we look at the plot on the left-hand side here, this is a density contours, and this is an MD simulation generated with FlowMo, which is an open source software for molecular dynamic simulations. You can download it from this GitHub repo. And so we have basically the red region at the bottom of the domain is a wall, and there is a cavity within the wall. And as we introduce some heat into the system, at some point you will see some vapor generated inside the cavity, and this vapor region keeps growing as more heat is introduced into the liquid domain. On the right-hand side, you can see the temperature field. And once the bubble is large enough, we can fit a circle at the interface and look, for example, at the radius versus time and how it evolves. For those of you who are not familiar with MD units, in this presentation, all the results will be in non-dimensional MD units, so you can use these conversion factors to convert them into standard units, for example. So a length of 1 in the MD domain corresponds to 0.34 nanometers, and temperature of 1 is around 125 Kelvin, and density 0.7, which is basically the density of the liquid, is not too far from the density of water, for example. Right, so if you look closer at the cavity, the size of this cavity is around 21 nanometers. And again, we can look at the density field. So initially, it's entirely filled by liquid, and then after some heat is introduced, the temperature reaches the saturation value, then a region of vapor is generated and keeps growing and propagates into the liquid domain. The fluid that we use here is argon. So how do we set up this case? Well, first of all, this is a one-way coupled simulation, which means that we first run an empty simulation. We store data into several snapshots. When I say data, I mean, for example, the velocity field, temperature field, and density. And then we run CFD. So CFD runs after MD and is coupled with MD through some sort of time-dependent boundary condition. So if this is our entire domain, let's say we split this domain into two parts with this horizontal line, and we solve the continuum simulation. So the CFD domain exists only above this line. But anyway, we still have the information, the data, the field in the bottom region from the MD simulation. So this dotted line appears to be the boundary between the two worlds, and this is where our coupled boundary actually exists. So at this boundary, we need to read data from the MD and pass this information to OpenFOAM as a time-evolving boundary condition. So for this specific example, data is read every 10 time steps, so which means that we run CFD for 10 time steps, and then we update the values of momentum, so the three components of the velocity field, temperature, and volume fraction of the liquid from the MD simulations. Now, momentum and temperature are readily available from MD, but to run a two-phase simulations with OpenFOAM with a BOF method, for example, we also need the volume fraction of liquid. Now, this is not readily available from MD, but we have the density from MD, so there exists a number of ways to get the alpha, so the volume fraction of the liquid from the density field. One approach is to use the VRF equation, so rho here is the density from the MD domain that we have here, and rho V and rho L are densities of vapor and liquid from the CFD simulation. So these two are constant values as we use an incompressible solver, so we keep them constant. Another approach, which is, by the way, the one that we use in this example, is to define a threshold value and say that whatever is above this threshold value is liquid. And so we set the volume fraction of liquid to 1. Whatever is below this value is assumed to be vapor, and so volume fraction of liquid is 0. The other boundaries, boundary conditions, are standard CFD boundary conditions that are already available in OpenFOAM. So we go periodic from left to right, and also from front to rear, because this is a 3D actual simulation. And on the top boundary, we put a zero gradient boundary condition. Right, so let's have a look at the files that we need to edit. This example is available in this in the GitHub repo of CPL OpenFOAM. So under examples, interFOAM hard phase change, which is the name, just the solver that Mirco presented you before, and it is the one that we use to run this application. So in this folder, you have all the files that you need to run this case, apart from the MD data. I'll show you later where you can find the MD data. And we also use a PyData view that was introduced in previous talk, and this is used to load the MD data, and you can git clone from this repository. So in this tutorial, you have already done this in your work directory, so I want to show you how to actually clone this repo. Right, so in order to set up the CFD simulations, for those of you who are already familiar with OpenFOAM, this is the standard tree structure of any OpenFOAM simulation. So we can start from boundary conditions, for example, in the 0 time step folder. And basically, for all the boundary variables that we solve, like momentum, temperature, and volume fraction, you will find the CPL receive MD boundary here, which is the a coupled boundaries at the bottom of the CFD domain, and they all take the same values. This is automatically handled by the coupling library. Next step is the mesh. Here we do simple Cartesian meshes. So you define basically the 8 vertices of your domain. And again, CPL receive MD is the bottom boundary, the coupling one, and these are the vertices that define this phase. So this is an horizontal phase, which has dimensions in X and Z directions. So the normal to this phase is along the Y direction. Then we need to set up the properties of our two-phase system. So this is specific to this solver. And in transport properties, which is within the constant folder, you need to set the properties of both liquid and vapor, such as kinematic viscosity, density. Again, all the units here are MD units, so the non-dimensional values. And kappa is the thermal conductivity in the energy equation, and HF is the latent heat of vaporization. We do the same for the vapor. And finally, on the phase change properties, you set up your phase change model. This is how the mass transfer rate is computed. For more information, you can refer to the applications that we have shown you before or to this one. And basically, the mass transfer is driven by the delta T at the interface, where T sat is the saturation temperature, which is set here. R is the ratio between the universal constant for gas and the molar mass. And sigma evaporation is the coefficient that we call here gamma. dm dot is used to basically spread this source term, which originally is only at the interface, into a few layers of cells. This is the Harden-Bonjour method, and this improves the stability and robustness of the solver. Finally, you need to decompose the domain because we're running a parallel computation. So we do with the method simple. And for this specific case, we only split along the X direction, which means that we will have 2 subdomains along X, and no splitting occurs along Y and Z directions. So the other file that you need to add is actually the script used to load and send MD data, as the name suggests. This is a Python script. And inside this script, you need to edit a few things. So first of all, XYZL takes the dimensions of your domain. So the extensions along X is LX here, LY and LZ. For this specific case, we have the same dimension along X and Y. And the thickness along the third dimension is much smaller compared to the other 2 dimensions. And then when you call the MD create Cartesian function, you need to give as an input the subdomains along the X, Y, and Z direction. So in this case, again, we only have 2 subdomains along Z direction, but we don't have any splitting along Y and Z. So this is why you see 2, 1, 1 in this function. Within the same script, the core part is basically a for loop that loops over the time steps. And every 10 time steps, in this case, we need to go back to the MD data, read a new snapshot, and update the value at the bottom boundary of the CFD domain. So we do this for all the fields that we need to update, so density, momentum, and temperature. And what you see here as MD raw, for example, is the density field from the molecular dynamic simulations. But of course, we don't need it everywhere, but we only need it at the boundary between the CFD and the MD, and this is done here. MD raw BC is basically the average of this field at this plane. So Y equals Y log is the horizontal plane where the coupling actually occurs. And we do the same for momentum and the UBC, and for temperature and the TBC. Once this is done, we can send this information to the CFD to OpenFOAM basically, and we do that with the send array function. It takes 4 entries. The first entry is the field. We have 0, 1, 2 for the 3 components of velocity. 3 is for density and 4 is for temperature. Remember, the density needs to be transformed into owing fraction of liquid in order to be communicated in order to inform OpenFOAM. And the last 3 entries refers to the cells that where we apply this send array function. So if we look at the domain, at the bottom part of the domain, of the CFD domain, you see the coupled boundary is this horizontal face here, and these are the cells at the bottom boundary. So of course, we want to apply this information to all the cells at the bottom boundary. So this corresponds to all the cells along X, only the first layer of cells along Y, it takes the index 0, and all cells along the Z direction. Right, so once this is done, we can move to the recorded demo. So this is a video, and I will refer to this this guide that you have available on how to run this example. So first thing we need to do is to set up the default environments. Again, so we need to, after you log in into ARCHER2, you basically need to module load these packages and also to source these environments, the CPL app environment. So we do this here. So first we'll log in through SSH, and then we module load our software. Then comes the second package, the CPL OpenFOAM, and finally we can source from CPL app. Then, once this is done, if you go back to the index of this guide, you can look into the interFOAM hard phase change example, which is again the name of the OpenFOAM solver we're using for this example. And all you have to do here is to basically copy the corresponding example folder into your working directory. And once you go inside this directory, you see you have all the files that you need to run this application. So you will recognize the OpenFOAM folder, such as constant for the properties, or system for control dict, and find volume schemes and the other input files. So here we're gonna modify the Python script to load and send the data. So as I told you before, we rely on PyDataView to read the data. So you need to add a pp directory entry with the directory where you have it cloned your PyDataView application. In my case, it's this address. And then, of course, we need also to inform where the MD data is stored, because this file needs to go and look for MD data, and we do this here. F there is a directory of where you have stored this MD data. Finally, here you see start rec and end rec. These are just the number of the records of the MD. So we start reading at 455 up to end rec. Then you need also to edit the submission script, so called example ARCHER2 batch script. The first entries are basically standard Slurm commands. So we can, for example, increase the hold time to 1 hour and 10 as the simulation takes a while to run. And remember to change the account with your project code. So in my case, it's ECSEAF01. And since we use PyDataView to read the data, we also need to have a working installation. This is unfortunately no longer available on ARCHER2, so you need to follow this instruction here to basically install a virtual Python environment where you can have a local installation of matplotlib and other libraries. And once this is done, you need to source your virtual environment in order to be able to use matplotlib. So we need to copy this line in the submission script. Again, remember to change the directory and your username here. And finally, if we take a look at the srun command, this MD is an executable for a dummy MD application. So we're gonna replace this with our Python executable. So again, to execute Python, we call Python and then the name of the Python script. Right, so once this is done, we can submit our job through spatch commands. Make sure that our job is running, and when it is running, we can look at some of the log files generated by this application. So this is, for example, the log files of the mesh. You can have a look at the statistics, such as other information, such as number of cells, faces, and points. We can do the same for the log file of the parallel decomposition. So again, we have split the domain only in 2 subdomains along X direction. So we only have 2 processors involved here, processor 0 and processor 1, with the same number of cells, basically. And right, once we're happy with the setup of the simulation, we can have a look at the Slurm file. So OpenFOAM will basically output the log file into the Slurm /number of job ID file, and this is all the information that the solver brings as it runs. So we also have included a few post-processing functions in control D. So one of these functions is used to monitor the volume of the bubble. So you will find it in this directory here, post-processing bubble volume 0 folder. And you see, initially there is no vapor inside the domain. So on the first column is the time, and the second column is the volume of the bubble. It takes some time before the vapor to be generated before and then to be transferred into the CFD domain. So this actually happens when you are around 4,000 time units, a bit before, and then you see how the volume of the bubbles evolves. If you wanna plot this to arrays, you can, for example, use GNU-plot to have a look at the simulation as it is whilst it is running. So to use GNU-plot, you just module load GNU-plot, and then you have GNU-plot available in your section, so you can open GNU-plots and plot this file. On the x-axis, there is the time. On the y-axis, there is the volume of the bubble. So you see initially there is no volume of the bubble in the CFD domain, and towards the end of the simulation, this is how the plot should look like. So you see that the bubble is then keeps increasing because more vapor is introduced from the bottom of the domain, but also because there is a phase change. So there is some evaporation occurring at the interface, and so the volume of the bubble increases. This is all for this demonstration. Let me go back to my presentation. So let's have a look at some of the results. So again, this is the video you have seen at the beginning of today's talks, and hopefully now you know a bit more about this simulation. So again, in the empty domain, it takes a while before we see some volume of vapor generated, and once this reaches the bottom boundary, it is then tracked by means of a volume of fluid method in OpenFOAM. If we want to look at more quantitative analysis, we can, for example, plot the vapor mass versus time for the two cases. So the continuous line is the MD-only simulation. The dots represent the coupled simulation. On the left, you see a video where in the left-hand side, there is a representation of the coupled simulation. And on the right-hand side, you see MD-only data. So once the bubble enters the CFD domain, both from a qualitative point of view as well as quantitative point of view, we have a nice equivalence between these two simulations. Right, so my last slide will be about how to reproduce this example. So for those of you who have access to ARCHER2, I've put my the MD data under this directory. You should be able to access and copy the files from here. For those of you who don't have access to ARCHER2, you can still run this example using CPL Interform Hard Phase Change Solver, but instead of using the load and send MD data Python script, you can run this minimal MD Python script that doesn't actually read MD data, but rather injects a uniform vapor jet at the bottom. So you define the velocity component of the vapor jet here. These are only a vertical component. And within this for loop, you set for the cells between 60 and 90. We have like 160 cells at the bottom. So here we are basically in the middle of the domain. We set the density of vapor, and also we apply a vertical velocity to bring some vapor into the CFD domain. Outside this bundle, we only have liquid. You see the density is much larger than in the vapor region. And also we do not apply any vertical velocity component. So we are not injecting any liquid into the domain. So in this way, you don't need to have access to MD data. You can just rerun this example by assuming there is a uniform jet of vapor at the bottom of your domain. And this was my last slide. So I'm done. And I think we can open the floor for questions.
Thank you, Gabriele, for your part. I guess now it's back on me. Thank you, Gabriele. Thank you, Gavin. Thank you, Ed, for all your talks. And so the plan now is to go through the questions that you have posted in the Padlet. And we will answer to the questions now during the session. When we are done, we will interrupt the recording, and anyone is free to unmute the microphone and ask the questions directly to us, so that we can have a nice live discussion about what we've been seeing so far. So I'm now going to go through the questions in the Padlet. For those of you who joined later and cannot see it, I'm going to put it here in the chat. so that you have it here at the bottom of the chat. You can click on it. So I'm not going to share my screen for now unless it's strictly necessary to answer your questions. I'm going from the top, and the first question I see is how to define initial and boundary conditions for MD and CFD. This was a question posted really at the beginning, so I guess this has been answered clearly for what concerns the CFD part, at least. So the boundary conditions and initial conditions, they really come from the CPL send and receive commands, and you have seen how to specify the boundary in the 0 folder, how to specify the specific boundaries. I don't know, Ed, if you want to add anything about how to specify them in the molecular dynamics.
So initial condition in both codes are essentially just how you set the code up. So they are completely separate, and the only coupling between them is that bottom boundary condition set on the CFD side from the kind of average of the MD. And on the MD, your initial condition, normally you would run it for a period of time to kind of equilibrate before you even turn the coupling on. So again, your initial condition there would be set up in the usual way. So both codes you can kind of set up the normal initial conditions, and then the boundaries. Yeah, I mean, I think certainly hopefully it's clear for the MD side, it's the force, and then really just the force applied at the top, and then for the CFD side, it's just the average of that region that's applied back as the boundary for the CFD.
Okay, thanks, Ed. And to whoever posted the questions, if you're not happy with the answer, if it's not clear, feel free to unmute the microphone and speak when we are done with responding to these questions here. Ed, I carry on with the questions that we have in the Padlet, because the next ones are those that we received in the sign-up form. So I'm going to go ahead and read those. And the first one that I see is, I would like to learn a coupling, simplest example of coupling so I can apply it to my cases. For instance, coupling of OpenFOAM and MD in a lid-driven cavity with slip velocity at the wall, and have some demonstration of the coupling. I suppose, so these were the questions that people have put in the registration form, and these hopefully have been already answered during the talk by showing all the Couette flow and boiling sample cases. If not, feel free to let us know.
Just a quick one on that. I mean, so Couette flow I think is a slightly simpler case than lid-driven cavity. There is actually a couple example of lid-driven cavity back in 2004 by Ni, Chen, E, and Robbins, and so that case would be possible to set up in the same way. But you know, it would essentially be Couette flow, but you just put walls on for your MD case and for the CFD case.
Thanks, Ed. I move forward to the next questions, and I think, Ed, I will still need your help. So the next one is integration, new cases. So if it's possible to comment on the ease or difficulty of integration of coupling library with existing tools.
So part of the logic for showing the kind of minimal examples is to show how you would then do that for your own cases. And so just the kind of getting a new code linked in is as simple as that kind of couple initialize, set up, send and receive. You would need to have a Cartesian communicator, an MPI Cartesian communicator. So that's one of the requirements. But you could set that up yourself if you haven't got it, that this sort of mirrors the topology of your code. But provided you've got those pieces, it's about 4 or 5 arguments that need to be passed to the function, and then you just need to link in the shared library. And there's probably enough examples with the OpenFOAM case and the LAMMPS case to be able to kind of build on that. But if there's a particular application someone has in mind, please get in touch. I'm always interested to know what can be done and help out extending it.
Thanks, Ed. I move forward. How to go from scratch to a multi-scale simulation and apply the software to problems of my choice, including things to keep in mind, etc. And well, I guess we have prepared the documentation on how to do this, so how to install everything. And I suppose that the 2 test cases that we have provided are a first walk-in introduction on how to set up for the Couette flow case and the boiling flow case. So that it could be a first starting point to how to go from scratch to a multi-scale simulation. Ed, do you have anything to add to what I just said?
No, that sounds good. I think we've covered that. If we haven't, please let us know.
Yeah. Next, a couple of comments on the boiling side. Someone is asking about simulation of cavitating flows. So I would simply say that if we have coupled the solver for boiling, the one that we call the CPL interfoam hard phase change, you can actually couple any kind of other solver. So if you have a solver for cavitating flow, so for example, based on the volume of fluid method, but calculating the phase change rate based on some physical laws pertinent to cavitation, you can absolutely do that. As you have seen, the only extra bit we have added to a boiling solver has been all those blocks of the CPL where you have the initialization of the exchange of information, initialization of the CFD MD field, and the transfer of the boundary conditions at every time step. So provided that you just copy paste those blocks, this should work for any other case, provided that you set up your CFD solver to solve the right equation and the MD solver to solve the right physics. Ed, I don't know if you have anything else to add, feel free to do it.
No, I think you covered it.
And there is another question about CFD analysis of a boiling of a fluid in a microchannel. This is a little bit the same. So the difficulty is how do you want to couple the domain between MD and CFD? In that case, I can imagine that the CFD would be a more elongated domain, and we want to have, having an elongated domain also for the MD becomes a bit tricky because you need to cover the entire surface area of the CFD. So if you just want to add, for example, a nucleation spot, and you have the CFD solving the flow, and the molecular dynamics enters only in one specific point, that's possible. It will require a bit of adjustment of the architecture because the two domains will not share the same boundary. The MD will be a smaller boundary in the CFD. There is another follow-on question, how hard it would be to use this coupling method with LAMMPS optional granular package. I don't know, Ed, if you covered this during your talk?
Hopefully. I mean, so the last ECSE project was actually to develop the coupling for granular mechanics. So there's actually quite a lot of functionality already built into that. So, I mean, if anyone's actually interested in that, please get in touch and I can explain in more detail. But I think the majority of people are more focused on the kind of boiling applications. So we should probably not go too far down that rabbit hole. But it is really just a special case where you completely overlap and your molecules are particles. And then a lot of the same machinery can just be used in a slightly different way.
Thank you, Ed. I moved further down the Padlet. Quick question. Precise is kind of famous in the OpenFOAM world for coupling codes. Out of curiosity, do you happen to know how, if it could also work, or is there an advantage to CPL? Thanks for the webinar. Ed, I leave you the answer.
Yeah, so I mean, part of this is historical. So, as I said, this has been going for maybe more than 10 years. And so before, when I started working on Couple Library, I didn't know Precise existed. I don't think it was certainly as easy to find software back then. So part of the answer to that is historical. So I think, if I was starting again now, I probably would have used one of these libraries that's kind of well supported. The other one is specialism. So, Precise is for fluid structure interaction mainly, and whereas this Couple Library has been developed really for MD and CFD coupling, it's also for uniform grids. So Precise is a very general purpose solver that allows you to link kind of finite element solvers on unstructured grids to anything else. Whereas Couple Library, we really focused on using these Cartesian topology. So the MPI Cartesian topology, assuming a uniform grid on both sides, and linking the two together using those. So the idea is you get better scaling that way. You've got simplicity, and you've got your kind of coupling being a very uniform setup. The justification for keeping something that is, you know, arguably kind of limited but simple is that most of your MD cases you're actually averaging on a uniform grid anyway. So actually that point of exchange will be uniform anyway. And then there's nothing to stop you having a kind of unstructured grid in the rest of your CFD, provided your boundary condition is uniform. So, you know, the idea here was that if you wanted to go to a more complicated CFD case, you would keep a uniform boundary condition with a uniform structured grid. You get all the benefit of the kind of one-to-one mapping that you get from the, you know, Cartesian decomposition of the MPI topology and the kind of simplified coupling there, and then you can do whatever you want on the CFD side. So that's really our kind of niche that we're kind of focused on with this library.
Thanks, Ed. I carry on. How does one establish how large the overlap between the CFD and molecular dynamics regions needs to be? Now, I can answer this question saying that, very good question. There are actually journal papers out about it, because the principle of coupling MD and CFD is not new per se. So there are people who have done it before, and there are publications where essentially it's the buffer region that needs to be large enough to avoid feedback between the two. So what I remember is that people have done some kind of systematic study changing the number of cells in that buffer region to make sure that there is no feedback, and above a certain number of cells or above a certain height of that overlap region, there is no longer an advantage in keeping increasing that. So if anyone, the person who made the question, if you want to get in touch with us, we can point you to the right publication where this was explained. Ed, unless you have anything to add, I carry on.
No,
Are there any thoughts on how to efficiently generate inputs for the coupled approach that would enable the morphology of a real surface to be represented in the molecular dynamics domain? For example, the surface profile including roughness and possibly the subsurface microstructure that would impact active nucleation site in boiling simulations. Well, this is eventually where we would like to arrive at the end. So for sure, we would need the morphology of a real surface. So either from detailed AFM or SAM scan of a surface, or generated by a random generator. I don't know, you know the average surface roughness, you know the peak to valley average height, and you have like a random generator of a surface. Now, how to bring it in the coupled code, we haven't thought through all the details yet, but our initial idea is, for example, to really coat the surface with a molecular dynamics domain, a small one that coats the surface, whereas all the rest of the domain is covered by the CFD. So that we didn't get there yet. We would like to get there, but these are our initial thoughts about it. And moving down, can the CPL...
Just to mention that the other thing is that with LAMMPS, you know, you can design any surface shape you want by essentially setting up an FCC lattice and then just cutting away and leaving behind that surface structure. And within LAMMPS input syntax, there are pretty sophisticated ways of doing that. So you could specify, you know, that you want a kind of lattice design, and you, within the input syntax, you can design those surfaces. There's also codes like mol-template that make it very easy to kind of design different molecular systems. So you know, certainly at the molecular level, there are lots of tools that are available to kind of build and design surfaces at that kind of molecular shape. In terms of automating it, I know there's a tool by James Ewan at Imperial. We designed one for tribology applications and automating the kind of different roughnesses and chemical structure. And I know there's a few others that essentially work to do that. So there's certainly, because obviously lots of people who work in material science have done lots of work on building surfaces. So, you know, we're planning to kind of piggyback on that when we get there.
Thanks, Ed. Next question is for you again. Can the CPL deal with multi-species cases? There might be some species exchange in the buffer zone.
So at the moment we're doing volume of fluid, and the multi-species is handled by passing the density boundary condition. I mean, in principle, you can pass any boundary condition you want, and it would just be a case of just packaging up some average property from the MD and passing it to the CFD. I guess it depends on how you're actually describing the species, but you know, as long as you from the MD can average it in some way to get a quantity that can be passed into a form that the CFD can understand, it really is just a kind of averaging and transfer problem. Yeah, I don't know if Mirco, you got anything else to say on the kind of different models for multi-species?
No, well, I think you covered everything.
Can I add something on this? Sorry.
Go, Gabriele, of course.
Yeah, just wanted to say that from the CFD point of view, if you have species transport, all you need to know is the concentration of the species at the boundary. So if you can get that from the MD, then you can just solve multiple transport equations for all the species you have. And this is as long as you assume that the density is within the bubble is not dependent on the species concentration, and you can keep working with an incompressible solver by keeping the density the same. Of course, if you have highly non-uniform species, mixtures, then maybe moving to a compressible solver or adding some correction terms into the continuity equation to take into account how the density changes according to the composition of the mixture probably is something that needs to be taken into account.
Thanks, Gabriele. Thanks for clarifying that. Next question we have is, what is the actual scale of your continuum simulation? Is it congruent with molecular dynamics, so angstroms, nanometers, or is your scale much larger, solving the multi-scale problem? I can answer this question just based on what Gabriele showed. The scale is for now set by the molecular dynamics. So the CFD is actually using the same scale. So we were limited to a domain on the order of 100 nanometers or so in your simulation, Gabriele, if I remember well. Potentially, the CFD domain can be made much bigger. So there is no restriction with that. To solve really the multi-scale problem, then we would need also to address that time step coupling, which for now, let's say, is the molecular dynamics that is fixing the time scales. Ed, Gabriele, do you have anything else to add to this?
Just that the purpose of coupling reduces a kind of 3D problem down to a 2D problem. So something that costs, you know, however much for 3D simulation, you can reduce just to a thin slab by the wall. So you essentially can get much bigger, but yeah, you are limited to those LAMMPS scales. And then the next step in this would be some sort of clever switching on and off of the MD domain. So ideally, you'd run the MD until you got nucleation to the size that it could be kind of handed off to the CFD, and then you would turn that off. And so by doing that, maybe you can kind of transcend that, and then with a mixture of grid stretching and other techniques, essentially get past that. But certainly, this is one of the kind of active research topics in the area.
Next question we have, how LAMMPS is using the temperature information received from OpenFOAM side? Well, Ed, I guess I can just respond to this one saying that we don't have yet the two-way coupling that takes the temperature from OpenFOAM to LAMMPS. Am I right in saying so?
Yeah, and even in the coupled Couette case, I mean, you could, if you wanted to, apply energy coupling. And certainly the later papers on flux coupling, they add a thermostat or an energy constraint. In the case I've got there, I don't, and I don't do the energy transfer back. But you could do it quite easily using the thermostat mechanism within LAMMPS. And so what you do is you'd pass the temperature of the CFD back, and you would apply a local thermostat in a particular region of the MD domain. So that would be like another constraint force. It would be a thermostating force if you wanted to do that. Currently, we don't.
Then we have, are there any restrictions on mesh topology? For example, uniform or non-uniform mesh in OpenFOAM. Similarly, are there any restrictions on the decomposition method to use? So I can say that in principle there would be no restrictions, but the way for now we have coded everything, I assume we need to have regular and uniform meshes made of cubes. Am I right, Ed? Even though potentially this can be extended to any kind of mesh.
Cuboids, yeah, but and essentially uniform decomposition into processors. So, you know, you've got integer number of processors, so integer number of cells per processor, and so on. So it's that kind of uniform decomposition. You know, certainly all of this could be changed if there was interest in doing that. But it's, you know, again, it's simple enough just to set up that, and it's not too restrictive in our experience.
How well does a one-way coupling work for subcooled boiling cases, since there is circulation of vapor within the bubble? I can answer this to say that yes, well, the one-way coupling, of course, it works only when we have a unidirectional flow from molecular dynamics to CFD. If there is any circulation so that there is mass from the CFD going back to the MD, we need a two-way coupling that and we don't have it yet. So just to say that if delta fluid dynamics structure that impact the flow, then because it's not captured, it may limit the reliability of the simulation. And I guess this question is, the next question is also related to that. Are there any plans for demonstrating two-way coupling? And well, there are plans, of course, but I would say that the next step of this work. So far, the two-way coupling is already demonstrated with the Couette flow. We are looking forward to move this to the next step, also to have the same with the boiling case. What CFD solver was used for the turbulent flow example shown? Ed, I guess this is a question for you. You showed some turbulent flow example at the beginning.
Yeah, it was just OpenFOAM in that particular case. The justification for doing this, by the way, I ran an MD simulation at Reynolds number 400, and you can show turbulence in a kind of pure MD system. And I took the original initial condition from that pure MD simulation from OpenFOAM. So the two systems do the same thing, but any CFD solver will work. And in the past, I used Channel Flow, which is a spectral solver, as well as an in-house one. So that turbulent case you could couple to any any CFD solver should do that.
Thanks, Ed. I move forward because we need to finish with the question soon to close the recording, the video recording. Some might argue that water is less widely studied using MD than gases like argon. Are there challenges or barriers to applying this coupled approach specifically to water? Ed, do you have anything to say? I don't see any particular challenge as long as you have the right molecular potential models.
Yeah, I mean, the long range interactions are potentially a bit more complicated. We started looking into this, and the actual practical aspect that the water is just much slower simulation times for coupling really stopped us. But yeah, there's no reason you couldn't do this. You know, water behaves. You know, you'd average water in the same way, you'd pass the velocity up, you'd apply the constraint in the same way. So there's no reason why this particular constrained method would not work.
How long did the demo boiling case take to run using 2 cores? Gabriele, I guess it was very...
If I remember correctly, something between half an hour and 40 minutes to load all the MD data that we have available.
Yeah, I guess the bottleneck there was the MD simulation that had to run first.
Yeah, exactly. Yeah. I'm just think the length of the duration of the CFD case. Yeah.
And just to complete that, the MD case was run on about 40 cores, and it took, I think, about 72 hours to get through that whole nucleation process, including a bit of time before where you're waiting for it to nucleate. So if you put it on Archer, and typically we would make the MD a very large number of cores, you know, you should be able to get parity in the kind of timescales, hopefully.
Last question, in order to have perfect coupling, does one need to have transport properties, viscosity, heat conductivity, as a continuous function of the temperature which completely corresponds to those MD gives? Because MD gives non-constant temperature at the overlap due to fluctuation, especially for boiling with a drastic change. So ideally, we want to have the properties of MD and CFD to be exactly the same at the overlap between the two. So ideally, we would like to have the CFD properties to have the same function of temperature as the molecular dynamics, even though the current format of the solver that we have has constant properties in the CFD side, but it shouldn't be too problematic to have temperature-dependent properties in the CFD with some polynomial functions that are tuned based on some MD pre-simulations to provide those properties. Ed, do you have anything to add to this?
No, exactly that. I think the thing to just mention is a kind of implicit assumption in doing this coupling that at the point where they couple, the CFD is a pretty good approximation for the MD. And so that's why if it's not, if you have those kind of strong temperature dependent, say surface tension's a particularly temperature dependent one, and you've got strong enough temperature gradients, then yeah, maybe you need to consider supplementing your continuum model to make it more sophisticated. I think that the real test for all of this is you run the MD case by itself, you run a CFD case with coupling, and you compare the two, and you're checking to make sure that the coupled case is doing the same thing. And the real way to get them to do the same thing is make sure you've got the same coefficients between both, which is kind of where we are now, right? Trying to get the two to agree, because for exactly that reason, it's sometimes you get this kind of non-linearity in those.
Thank you very much, Ed. Thank you very much, Gabriele, for your answers. We got at the end of the set of questions that were posted by the audience. So at this point, we can interrupt the recording